Okay, thank you for coming to this week's GOCC. This week we have Melissa Sherman-Bennett from UC Davis giving an expository talk on the combinatorics of the amplituhedron. Our community guidelines are we are all learning, everyone has something to contribute, and no one has all the answers. So with that, take it away, Melissa.
Yeah, so thanks a lot for the invitation. Yeah, so I'll be talking today about this mathematical object called the amplituhedron. And it's a fairly young object. It was defined in 2014, so about 10 years old. And so actually, like any expository talk involves actually sort of probably some research too. So I'll be talking a bit about some joint work on this topic with Chaim Even-Zohar, Tzvika Lakrec, Matteo Parisi, Tessler and Williams, or subsets of those people, kind of a series of papers. I'll get to this at the end. Most of the time, we'll be talking about the amplituhedron, what it is, what the main question is, and kind of why that's the main question. Right, and I should say, please stop me for questions at any time or ask me to define things if I haven't defined something you want to know about. I can see the chat, so that's also okay, but I also encourage you to unmute if you want to. Okay, so I'm going to start out with the definition of the amplituhedron, and it's going to take a little while. So before I talk about the amplituhedron, I need to talk about another mathematical object called the totally non-negative Grassmannian. And this is going to be kind of sitting in the background during the whole talk. Okay, so first, just some kind of standard notation. And all right, the just usual Grassmannian, GRKN. This is the set of k-dimensional subspaces in R to the n. And I like to think of this space instead as the space of full rank k by n matrices modulo row operations, right? And so, okay, the way this correspondence works, I pick a full rank matrix A, I'm thinking of it sort of modulo row operations, and this just represents for me the row span of A. Okay, I often will sort of conflate these matrices with their row span, so just keep that in mind. Okay, so I'm going to think about the Grassmannian endowed with some coordinates called Plücker coordinates. And these are indexed by k element subsets of n. So pick one of those, call it I. The Plücker coordinate delta I of V is going to be the maximal minor of a representative matrix for V that's located in column set I. Right, so I'm just taking the square submatrix of A, which is in exactly columns I, and then I'm taking that determinant. That's the Plücker coordinate. Okay, so they're called coordinates because they really are coordinates. So if you know the Plücker coordinates of V, then you know V. You can recover V. But there's a slight subtlety, which is that when I defined this Plücker coordinate, there was a choice involved. I chose a representative matrix, A, for my subspace. And actually, the Plücker coordinates are not quite independent of that choice. What happens if you change your representative A is that you rescale all Plücker coordinates by the same number. Okay, so instead of being sort of like honest coordinates, putting the Grassmannian inside of like R to the n choose k, they're projective coordinates. So they put the Grassmannian into projective space with n choose k coordinates, which is dimension n choose k minus 1. Okay, and I'll just give you a warning. So even though we think about the Grassmannian inside of this very large projective space, it's quite low dimensional because the Plücker coordinates actually satisfy loads of relations. The relations that they satisfy, well, they're called Plücker relations, and then all the relations generated by those. Plücker relations are quadratic, and sort of the simplest one looks like this. So this is the 3-term Plücker relation. It's for GR24. Remembering exactly this relation won't be too important. It's just sort of important to remember, yeah, we're taking sort of this ambient projective space, and then to get the Grassmannian, we're cutting by all of these quadratic relations. And so we're getting, in particular, some sort of curvy, low-dimensional space. I'm just gonna say it again. The Grassmannian is very curvy because, quadratic things that, like the solution sets of quadratic equations are very curvy. Okay, the one exception to this is that if I'm looking at GR1n, so this is the space of lines in R to the n, okay, well, that's just actually projective space of dimension n minus 1. So that one's not curvy. That one's honestly projective space. All of the other ones are curvy. Okay, so that's the Grassmannian. And now I want to put this adjective, totally non-negative, out in the front. So this definition is due to Lustig, who used pretty different language and was sort of in a more general setting. And then independently, Postnikov gave exactly this definition. So the totally non-negative Grassmannian, or TNN Grassmannian for short, is just the subset of the Grassmannian where all Pluker coordinates are non-negative. Right, so the Grassmannian is in this high dimensional projective space, and I'm just going to intersect it with the positive orthant, closed positive orthant, non-negative orthant, inside of this big ambient projective space. So yeah, maybe, right, so I guess I'll just say again, even though these equations that cut out the totally non-negative Grassmannian inside the Grassmannian, those guys are linear equations. The Grassmannian itself is curvy, so the totally non-negative Grassmannian will still be curvy. Having said that, I will draw for you not a curvy picture. So here is an example of TNN GR13. Okay, so GR13, right, that's lines in R3. So that's the same thing as P2, which I'll just draw as a plane. And the totally non-negative Grassmannian looks like this. Okay, so GR13, right, we said our representative matrices are going to be, well, in this situation, they'll be 1 by 3. So they'll just be like a single row. And then Pluker coordinates, those are the like maximal minors of this matrix. They're just going to be entries. So total non-negativity is saying my subspace is represented by a 1 by 3 matrix with non-negative entries. That's the only condition. And that space looks something like this. So you have some points, like this point here, where all Pluker coordinates are positive, right? And you sort of have a two dimensions worth of those points. And then you also have some other points where, say, one coordinate, maybe the middle coordinate is 0, and the other ones are positive. That will sort of give you this open edge here. And then you also have some other points where exactly one Pluker coordinate is positive, like this one where the middle Pluker coordinate is positive and the others are 0, and that gives you just a point's worth. So just kind of one point like that. Okay, so that's the picture of the TNN Grassmannian, the only one I can draw. I should say maybe if I changed this from a 3 to an n, then what I would get is not a triangle, but a higher dimensional simplex. So the natural generalization of this picture. And then if I change, right, if I'm thinking about n, but I change this to a k, then I get something I can't draw and also will be curvy. Okay. So this is the object that's kind of going to be sitting in the background. We need a little bit more information about it before going further. So kind of from this picture, and maybe just thinking about it, the totally non-negative Grassmannian, you can see it has a very natural stratification into pieces according to which Pluker coordinates are positive and which ones are 0, right? So the piece where all the Pluker coordinates are positive was this kind of open triangle here. And then like, you know, the piece where the last Pluker coordinate is 0, but the other two are positive is this open line segment. Right, and so that's true in general, right? You can do it for any kn, just collect together those points in the totally non-negative Grassmannian with the same positive 0/0 pattern of Pluker coordinates. So those pieces, I'm going to call these positroid cells. This index M here is just exactly the index sets of the Pluker coordinates that are positive on that cell. And then all the other ones should be 0. Yeah, so what should I say? So the word positroid is a portmanteau of like positive and matroid, if matroid is a word that is meaningful to you. If it's not, it doesn't really matter. And it's no accident that when I started talking about this, Like first I said, break the Grassmannian up into pieces. And then I said, oh, the pieces are called cells, which is a word with additional mathematical meaning. These pieces are actually homeomorphic to open balls. So you can see that here, right, where like the largest piece was this open triangle, that's definitely homeomorphic to an open ball. Yeah, and I should say, so that result that these pieces are open balls is due independently to Postnikov and Reach. Okay, so this is great. We have a space that we defined. It has this very natural decomposition, which is already well behaved, right? It's a decomposition into open balls. Things get even better. It turns out that this decomposition is what's called a regular CW complex, and the whole thing is homeomorphic to a closed ball. So this is a result of Galosh and Karpin-Lamb. They used sort of a result of Williams, which showed this was true combinatorially, and then they sort of upgraded it to a geometric statement. Okay, so what does this mean? Okay, so homeomorphic to a closed ball. Topologically, it's just a closed ball. This regular CW complex stuff is saying, basically, when I take my individual open balls, my cells, and I glue them together, I'm doing it in basically the most straightforward way possible. I'm not doing like, I'm not doing any kind of like funny twisting on the boundaries of the balls to put them together. I'm just really just like plopping them together. Yeah, and another thing that this tells you is that if I just take one cell on its own and look at its closure, I get a closed ball already. So like nothing funny is happening on the boundary ever. And okay, the thing you should keep in mind, like kind of the thing you should have in mind, is this is telling you that the totally non-negative Grassmannian is polytope-like. So it's not honestly a polytope because it's curvy, but sort of topologically speaking, kind of even combinatorially speaking, it has all of these nice properties that you would expect from a polytope. Okay, so that's the object that's going to be sitting in the background. And now we're going to hit this very nice object, the totally non-negative Grassmannian, with a map, and that will produce for us the amplituhedron. Yeah, so actually maybe I'll stop here and pause. Any questions about the totally non-negative Grassmannian? All right. Okay, so the amplituhedron was defined, like I said, around 2014 by two physicists, Arkani-Hamed and Trnka. So they were interested in scattering amplitudes. That's where the amplitude comes from. I'm not going to say much about this, but what scattering amplitudes are. So they're functions of, okay, so you have n particles moving around. They're functions of the momenta of those n particles, so exactly how those particles are moving. And the output is going to be the probability that the particles have interacted in some way, so like collided and then scattered in some manner. So that's what Arkani-Hamed and Trnka were interested in computing. And in the course of understanding these amplitudes, they cooked up the amplituhedron. And I'll talk more later about how they got here. Okay, but for now, just the definition. So I'm going to fix 3 parameter values, k, m, and n. And I'm also going to fix a helper matrix Z. So this is going to be an n by k plus m matrix. And the way that I choose my parameters, Z is going to be kind of tall and skinny, like this. And my matrix Z, I'm going to ask for the maximal minors to be positive. Okay, so the largest square submatrices, they should have positive determinants. Okay, so this helper matrix Z is going to induce a map on the totally non-negative Grassmannian just by matrix multiplication. And I'll call that map the amplituhedron map. Okay, so what it does, you start with a point in the totally non-negative Grassmannian represented by a matrix A, and then you send it to a point in a new Grassmannian represented by the matrix A times Z. Okay, and the new Grassmannian that this point is landing in is grk k plus m, because that's this will be a k by k plus m matrix. And you might be a little worried, like this matrix was full rank. It's not always true that when you multiply 2 matrices, you get a full rank matrix out, but the positivity conditions on both A and Z will ensure that this guy really is full rank, so it does represent a point in the Grassmannian. Okay, and right, so I said, right, so it's a map induced by matrix multiplication. That feels like a linear map. That is really true if you figure out the effect of of this map on the Plücker coordinates. So you write the Plücker coordinates here in terms of the Plücker coordinates here. You've done something linear. You've done like a linear change. Okay, so that's the amplituhedron map. The amplituhedron itself is just going to be the image of the totally non-negative Grassmannian under this amplituhedron map. So, okay, it's some sort of linear image of the totally non-negative Grassmannian. Okay, so before I tell you anything else, let me do some examples. So starting with k equals 1, and actually starting with k equals 1 and m equals 2. So what are the players in our game? So we've selected this matrix Z. It's a n by 3 matrix, and it should have positive 3 by 3 determinants. And it's going to induce a map from totally non-negative GR1n, right, which is a simplex, to totally non, or sorry, to just usual Grassmannian GR13, which is the projective plane. Okay, and how this map works? Well, I pick some point in here, right? So I pick something, like I basically pick a 1 by n matrix with non-negative entries. And then I just matrix multiply with Z. And so what I get is this linear combination of the rows of Z. Okay, so the rows of Z are vectors in R3, right? So if I were just thinking about like what I get in R3, well, I've got some vectors, and then I'm taking some linear combination of them where my coefficients are allowed to vary over like all non-negative numbers, right? So I'm taking all non-negative combinations of some vectors, and in R3, what you get is a cone, right? It's going to be the cone spanned by whatever vectors you're taking linear combinations of. And then since I'm in projective space, instead of thinking about this cone, I'm going to kind of slice it somewhere. And so when I have this cone and I slice it, what I get is I get a polygon sitting in the projective plane. And the positivity of this matrix, so the positivity requirements here, tell me that in this polygon, the vertices will be just the rows of Z, and those rows will sort of appear in counterclockwise order as I scan around the polygon. Yeah, so that's the amplituhedron. It's a polygon. The vertices of the polygon you read straight off of your matrix D. Sticking with k equals 1, if I bump up to arbitrary m, I will get something called a cyclic polytope with n vertices in PM. This actually follows from an older result of Sturmfeld's. Exactly what cyclic polytopes are, not so important for the rest of the talk, so I won't really talk about it. They're really nice polytopes. They're examples of polytopes that have the most faces in each dimension, given how many vertices they have, and what dimension they live in. And here's a picture for m equals 3. Okay, so whatever the amplituhedron is, for k equals 1, we just get a very nice class of polytopes. Some other examples, m equals 1. So this is work of Karp and Williams. So they show that the m equals 1 amplituhedron, well, you get it by taking a certain hyperplane arrangement, and then looking at the bounded complex, which is like the stuff in blue here. Right? So the hyperplane arrangement is the whole thing, and then the blue stuff consists of, well, those pieces that are bounded. Right, and the colored stuff here also is the bounded complex of this hyperplane arrangement. Okay, so k equals 1, we just got polytopes, a certain kind of polytope, and m equals 1, we're getting basically a certain kind of hyperplane arrangement. Both of those things are pretty linear, right? Polytopes are cut out by linear equations. These hyperplane arrangements, well, each piece is cut out by some linear equations. But k equals 1 and m equals 1, that's sort of the end of the linearity. So outside of k equals 1 or m equals 1, it's not usually going to be a polyhedron. Yeah, so just like the Grassmannian itself, it will be curvy. What I can tell you is its dimension is, well, it's going to be full dimensional in its ambient Grassmannian. So I didn't tell you the dimension of the Grassmannian, but okay, the dimension of this Grassmannian is k times m. Right, and just to like kind of double down on, it's not usually a polyhedron. For certain parameter values, the amplituhedron is actually just isomorphic to the totally non-negative Grassmannian. The z tilde map is an isomorphism. So in that situation, it's definitely curvy. Okay, and then, so what else can I tell you about it? Well, actually, just like really not that much. It's conjectured to be a cell complex. So conjecturally, you can break up the amplituhedron into these open balls, just like the totally non-negative Grassmannian. And it's also conjectured, I think, to be homeomorphic to an open ball, which is sort of known in, I'm sorry, homeomorphic to a closed ball. This is known in a bunch of special cases. So long list, but it's not, I should say like the techniques of all of these papers are very different. So there's no, yeah, it's not like we have an idea of how to prove it in general or anything. It's just we have some evidence for this conjecture. Okay, so that's the amplituhedron. It generalizes cyclic polytopes. It generalizes the totally non-negative Grassmannian. So one reason to study it, I guess, is just both of those things are really nice. And so you're studying a generalization. You hope it will also be nice or lead to some interesting stuff. That's not why the physicists were interested in it. So yeah, if there aren't questions, I'll just pause briefly. Okay, seems good. Then let me talk about kind of the question that the physicist asked. And since the physicist defined the amplituhedron, this was also the question that people have really been studying since the definition. Okay, so the idea is this. Okay, so we have the totally non-negative Grassmannian. We know if we hit it with the z tilde map, the amplituhedron map, we get the amplituhedron. But remember that the totally non-negative Grassmannian, it had a lot of extra structure. Namely, it had this very well-behaved cell decomposition into positroid cells. So one thing you could do is, well, you could take, instead of the whole totally non-negative Grassmannian, you could just take a single positroid cell or its closure and hit it under the z tilde map and ask about what you get. Another thing you could do, right? So you have this space up here that is stratified and you're hitting it with some map. You might ask, does the image kind of inherit a stratification from upstairs? And this is sort of the direction we're heading. We're gonna be interested in particular decompositions of the amplituhedron that are sort of inherited from the positroid cell decomposition upstairs. Maybe one thing I should say, I did not say this earlier, this space here is k times n minus k dimensional, and this space here is k times m dimensional. The way we chose the parameters, this number is always at least this number. So this linear map is going to squish a bunch of stuff, and that's going to be very important. So if we think about anything downstairs in terms of stuff upstairs, there's going to be like a lot of squishing. So we have to be sort of careful about how we think of things. Okay, so that being said, okay, so we're aiming for, so the first thing is just some notation. So if I take a positroid cell here and I hit it with the z tilde map, I'm going to denote that by z circ m. And then the closure is just going to be zm. Okay, and I'm going to care about decompositions of the amplituhedron into positroid cell images, these zm. But I'm going to restrict which zm I look at. So zm is called a tile if it's full dimensional in the amplituhedron. So it's k times m dimensional. And the z tilde map is injective on the positroid cell that we came from. Right, so what that means is for tiles, kind of their open part is just going to be an open ball, because how did I get it? I got it by taking an open ball and then hitting it with some injective map. Okay, so I will be interested in decompositions of the amplituhedron into tiles. So I'll call these tilings. And okay, tiling of the amplituhedron is a decomposition into tiles with disjoint interiors, right? So I don't want them to be overlapping in any big way. And yeah, kind of the central problem, like the big object or like the big focus of study so far has been to determine the tilings of the amplituhedron. So for one, it's not obvious that tilings exist. So part of it is like show that there are some tilings. And then once you know that there are some tilings, try to understand their global structure. Okay, so and like I said, the reason that this is a central problem really comes from the physics motivation. Before I talk about that, let me just give some examples of tilings so that you don't think that they're just like some really weird thing to be considering. So let's return to k equals 1. This was the situation, yeah, so k equals 1 and m equals 2. So this was the situation where the amplituhedron was just a polygon in the projective plane. And the vertices of the polygon were given by the rows of the Z matrix, and they sort of show up clockwise. Okay, so what are the tiles? Okay, so these are images of positroid cells. The image needs to be full dimensional, so it needs to be 2-dimensional. And the Z tilde map needs to be injective on the positroid cell that we were looking at. Okay, so let's just think about any 2-dimensional positroid cell and think about what its image is going to be. Okay, so if we've got, okay, so what does a 2-dimensional positroid cell look like? Well, it's row spans of matrices where exactly 3 coordinates are going to be positive, 3 entries are positive, and the rest are 0. So it's row spans of stuff that look like x1, x2, x3, and then a bunch of zeros. When we hit this with the Z tilde map, what do we get? Well, we get some linear combination of Z1, Z2, and Z3. Okay, so if I put that, so what kind of points am I getting? I'm getting some point in the interior of this triangle, right? And as I allow x1, x2, x3 to vary over all positive numbers, I'm going to cut out the whole open triangle. And then if I take the closure, I just get this whole triangle. So my tiles, they had this complicated, sorry, I should have said. Okay, so that's what the image of an arbitrary 2-dimensional cell looks like. It's a triangle. And then you ask, okay, is the Z tilde map injective on that cell? So if I pick some point in this triangle, can I find, like, is there a unique point that mapped to it from upstairs? And the answer is yes, right? So to find that point, what you do is you write this point as a combination of Z1, Z2, Z3, and that tells you what x1, x2, x3 must have been. Okay, so what this is telling me is that tiles are actually just images of arbitrary 2-dimensional positroid cells. The nicer way to say that is just that the tiles, like without talking about the positroid cells upstairs, the tiles are just triangles. They're just triangles in this polygon. And tilings are just going to be exactly the same thing as triangulations, right? So tilings, we want to decompose the polygon into triangles that don't overlap in their interiors. That's the same thing as being a triangulation. Okay. And this is not special to m equals 2. So if you look at k equals 1 but arbitrary m, when your amplituhedron is a cyclic polytope, your tiles will just be simplices, like on the vertices of the, yeah, so for example, the convex hull of these 4 vertices will be one of the tiles. And then tilings are going to be exactly the same thing as triangulations. And I'll just say, so we actually know a lot about the triangulations of cyclic polytopes. So these were characterized by Rambo in 97, and Hugh Thomas also has a very nice article about their combinatorics. Okay, so this is one way of saying like these tilings of amplituhedra are not crazy. In the cyclic polytope case, they recover something very natural, which is triangulations. Okay, so that being said, these tilings are not crazy. Why are we interested in tilings at all? So now let me talk about a little bit of the physics background. Not much, because I don't know much, but I'll give you the gloss. So, right. Arkani-Hamed and Trnka and other high-energy physicists want to compute these scattering amplitudes. There's a number of ways of computing them. One of the most efficient is what's called the BCFW recursion. So this is Brito, Cacciazzo, Feng, and Witten. And there's a bunch of different ways for running this recursion. So you can use this recursion to get many different formulas for a single scattering amplitude. So you'll get basically single scattering amplitude equals sum of lots of things, and different ways of running the recursion gives you different sums. But of course, they're all the same because you're computing the same scattering amplitude. And physicists were wondering, like, kind of what's the meaning behind all of these different formulas? Like, why, like, they look very different. Why are there why do they all equal the same thing? And Hodges in 2013 noticed that for kind of a specific class of amplitudes, the amplitude could be kind of interpreted as the volume of some polytope. And the different formulas for the amplitude really just corresponded to different triangulations of the polytope, in the sense that, like, basically, yeah, you could match up the different formulas with different ways of cutting your polytope into small pieces and then computing the volume of each piece and then summing them back together. And of course, the reason that you're getting the same thing out of those two different ways, out of those two different triangulations is, well, you're still just kind of decomposing the same set in two different ways. So of course, the volume of your big polytope does not change. And that's kind of why the formulas give the same thing. So Arkani-Hamed and Trnka were very inspired by this work of Hodges. And so what they wanted to cook up was some geometric object whose, like, volume gives the scattering amplitude, and different ways of breaking up this geometric object give you different ways of expressing the scattering amplitude as a sum. And they wanted this to sort of match up exactly with the formulas given by the BCFW recursion. So the amplituhedron was the geometric object that they cooked up to do this. So they conjectured that the volume of the amplituhedron is a scattering amplitude, and the BCFW recursion, all those different formulas, all that they're doing is giving tilings of the amplituhedron. Okay, so I should say now I've been saying volume in quotes. That's because, okay, it's not actually a volume. It's going to be some top degree differential form, but for all intents and purposes, like, the intuition is basically volume. Okay, so this this conjecture is basically the reason that the definition of tiling is the way it is. So if you have some big object and you want to compute its volume, what kinds of decompositions should you look at? Well, you should look at decompositions into full dimensional pieces that don't overlap. Okay, so that's part of the definition of tiling. And you also, like, this is not necessary, but it's useful. You also want your full dimensional smaller pieces to have computable volumes themselves, right? Otherwise, this decomposition will not help you. So that smaller pieces should have computable volumes. That's the reason why our tiles should be injective images of positroid cells. The idea is basically the positroid cells themselves have some computable volume. And then if you're just mapping it with Z tilde in an injective way, so not really disturbing it, then you should sort of also be able to understand the volume of the image. So that's the reason for that injective image condition. Okay, so this was sort of the central conjecture around the amplituhedron, like, it's why it was defined, kind of in the hopes that it would satisfy this conjecture. So this also guided a lot of the research on the amplituhedron for the last 10 years. At this point, right, so the original problem was just to prove the conjecture. So this has been done. So kind of showing that one way of running the BCFW recursion gives a tiling. This was done by Even-Zohar, Lakrec, and Tessler. And then all ways of the running a BCFW recursion giving a tiling, that was done with those three together with Matteo Parisi and Williams. I should also say this conjecture, we fix the M statistic to be 4 because that's the case that is relevant for physics. Okay, so that's the context of this conjecture. But sort of along the way, okay, so people were thinking about this conjecture. What's one thing when you have a conjecture that's hard, you like move to an easier version of the problem and try to prove it. So that's why we saw some early results on M equals 1. There's also a lot of progress on M equals 2 before this conjecture was solved. And in the process of looking at those somewhat easier cases, basically what came up is that the existence and combinatorics of tilings was of independent mathematical interest. So if you don't know anything about the physics, the existence and structure of the tilings already is very interesting. So that's sort of, yeah, so that's kind of been the main scope of the research on this thus far. Is kind of, there's been a lot of work focused on this original conjecture, but then also a lot of other interesting discoveries on the side, which say, even though the conjecture has now been solved, like the amplituhedron still worth studying, like still has some very interesting properties. Okay, so I'm going to pause here again to make sure that the motivation kind of makes sense, and then I'll talk about a little bit more about what I mean in this sentence.
Is there like a corresponding statement for values of M other than 4? And like, is it known if it holds?
To this sort of conjecture?
Yeah.
So there's no scattering amplitude interpretation. There are recursions to give tilings for M equals 1 and M equals 2. I have a guess for 1 and M equals 3, but it's not proved. So for higher M, it gets much more complicated. Yeah, even sort of, yeah, the recursion is like a good first step because it's at least like a concrete way to try to obtain tilings. And for M equals 4, we sort of like this group of authors, we tried for a long time with M equals 6, but it's pretty subtle seeming. Yeah. Yeah, so I should say actually existence of tilings is known for M equals 1, M equals 2, and M equals 4. M equals 3, there's this guess for a recursion. Okay, so maybe. And for higher M, it's like really unclear if the kind of notion of tiling needs to be tweaked. It's kind of stuff like that. So yeah, still very active and kind of a baby field still. Any other questions? All right. So yeah, so let me talk about some of the interesting combinatorics that comes out of this. So one very interesting piece of this story is the so-called magic number conjecture. Okay, so the magic number is going to be a certain specialization of the McMahon number. Okay, so the McMahon number depends on 3 parameters, A, B, and C, and it's defined as this triple product. But maybe more useful is to say that the McMahon number MABC enumerates loads of very interesting combinatorial objects. So one thing that it enumerates is C non-crossing lattice paths in an A by B rectangle. So here C is equal to 3, A is 2, and B is 3. It also enumerates plane partitions in an A by B by C box, or rhombus tilings of an A by B by C hexagon, or perfect matchings of a honeycomb lattice. And okay, how is this related? Okay, so this McMahon number somehow comes up in the study of the amplituhedron. So there's a conjecture that for M even, every tiling of the amplituhedron consists of a particular McMahon number of tiles, right? Where A, B, and C are chosen to be some numbers that depend on N, K, and M, the parameters of the amplituhedron. So this was a conjecture of Karp, Williams, and Zhang. So they sort of they had exists here, and then Galashan and Lamb were decided to be very bold, and they put a for all. Yeah, so this is, right. Let me just, as an example, kind of talk about, like, yeah, just to give a feeling for how kind of surprising this sort of property is, that all of the decompositions that we're looking at consist of exactly the same number of pieces. So, right, in a special case, the amplituhedron is a polytope, a special kind of polytope, and the tilings were just triangulations. It is usually really far from true that every triangulation of a polytope has the same number of simplices in it. So, okay, it's true on the plane, every triangulation of a polygon has the same number of simplices, but once you move up to higher dimensions, you get a really big spread in number of simplices in a triangulation of a given polytope. So already for polytopes, it's sort of special that the amplituhedron is a cyclic polytope, and the cyclic polytope has this, for M even, has this very special property that every triangulation consists of the same number of simplices. So yeah, this is like a very interesting kind of weird, kind of like a very interesting phenomenon. And then also there's this very nice combinatorial number showing up, which says the pieces should be in bijection with some of these really nice objects. Okay, so for the rest of my time, I'm just going to tell you a little bit about kind of what's known about the amplituhedron and its tilings. So, so I'm going to focus on m equals 2 and m equals 4. Really, probably m equals 2. So, okay, what do we know about the tilings of the m equals 2 amplituhedron? So, first of all, in that situation, we actually completely understand what the tiles are. So we understand exactly what pieces can show up in our tilings. We understand them in a number of different ways. We have a nice combinatorial indexing set. And we also have a semi-algebraic description of each tile. So this is like saying, right, so when we were talking about the polygon, we had a description of a tile that was like, oh, it's the image of any two-dimensional positroid cell from upstairs. We also had a description that was just like, it's a triangle in the polygon. This semi-algebraic description is like the latter. We're saying our tile is just some subset of the ambient Grassmannian, GRKK plus 2. And we don't have to talk about a positroid cell in the background to define this tile. We can just say it's this subset of GRKK plus 2 cut out by some inequalities. Okay, so we have kind of a complete understanding of the tiles in the m equals 2 situation. And we also have a complete understanding of the tilings in that there's a bijection between these tilings and certain decompositions of the hypersimplex. So I'll say a little bit more about this later. The hypersimplex is a polytope. And on this side, the decompositions that we're looking at are also polytopal. So basically what we have here is something that says for the m equals 2 amplituhedron, the combinatorics of tilings is the same as the combinatorics of some like linear problem, some kind of polytopal problem. So in that way, we have a complete understanding of the tilings for m equals 2 also. Okay, this sort of thing is really useful if you want to prove stuff about tilings. And in particular, you can use it to prove in m equals 2 that the magic number conjecture holds. So every tiling of the m equals 2 amplituhedron has this correct number, this magic number, McMahon's number of tiles, which in this case turns out to be n minus 2 choose k. Okay, and then, yeah, I mean, I'm not going to talk about this at all. I'll just throw this up there. So that was m equals 2. The main kind of state of the field in m equals 4 is we know that we can get tilings from this BCFW recurrence that comes from physics. There are definitely more of them, but we at least understand the ones that come from the kind of prediction, the physics prediction. And in this situation also, we can describe our tiles kind of not as images of particular positroid cells, but instead we can say, oh, it's just a particular subset of GRKK plus 4. Okay, so yeah, for the rest of the time, I'm just going to talk a little bit about these two results, probably mostly the first one. Yeah, okay, so if there aren't questions, I will. All right, seems like I'm good. All right, so first let me tell you about these tiles. Okay, so like I said, the first nice thing about tiles for m equals 2 is we have a good combinatorial indexing set. So tiles for m equals 2 are in bijection with pictures that look like this. So this is a properly bicolored subdivision of an n-gon with area k. Okay, so what do these words mean? Subdivision of an n-gon means I've taken my polygon and I've broken it down into smaller polygons without introducing any new vertices, right? So like this. Properly bicolored I've colored my smaller polygons black and white so that if two polygons share an edge, they're different colors, right? So I could not have colored this one black. That's not allowed. And then this area statistic is just keeping track of how much of my polygon is black, basically. So the way you compute this is you look at your black subpolygons. You just pick any triangulation you want of those. So like here's one. And then you just count the number of black triangles you see. So here I see 3 black triangles. So this is an area 3 example. Okay, so if you hand me one of these pictures, I can hand you a tile of the amplituhedron. So one way I could do that is given this picture, or like, yeah, so given one of these bicolored subdivisions, sigma, I could produce for you a cell of GRKN upstairs, and I can prove that the image of that cell is a tile. Okay, so that's and the exact way to come up with that cell is like not complicated at all. I'm just not really going to give it to you now. But the other thing you can do is you can start with your bicolored subdivision sigma, and you can just read off of that subdivision a direct description of the tile sitting inside of GRKK plus 2. And that's what I'll focus on today. Right. So to give this semi-algebraic description, it's going to be an inequality description. I'm going to say like, oh yeah, this tile, it's the subset of GRKK plus 2, where certain functions have a particular sign. Those functions are going to be a little different than Pluker coordinates. They're what are called twistor coordinates, which they're not very complicated. Okay, so what are twistor coordinates? Okay, so you have your point in GRKK plus 2. You have your matrix Z from the amplituhedron map. And you pick 2 indices, I and j and n. Twistor coordinate, I'm going to denote it by yij. And it's just the determinant of the matrix where I put y in the top. And then I put the ith row of z and then the jth row of z. Okay, and that gives me a square matrix. I take that determinant, that's the twistor coordinate. This is a linear function in the Pluker coordinates of y. It's useful when you want to describe the image of the amplituhedron map because it includes information about z, right? It has these 2 rows of z in there, so it sort of knows something about the map. Okay, so with that, let me give you this inequality description. So, right, so I've fixed my subdivision like this, and I'm supposed to describe for you the tile, and it's going to be a region where certain twistor coordinates have fixed sign. Okay, so I'm going to have one inequality. Okay, sorry, I forgot something. So the first thing you need to do is you need to triangulate the black polygons again in any way you want, doesn't matter. So maybe I'll pick this arc 2 to 6. Okay, and then for each arc of a black polygon, I'm going to have one inequality. And the way it goes is like this. So say I picked the arc 2 to 6. I'm going to write down an inequality like -1 to some sign times the twistor coordinate y26 is positive, right? So this inequality just tells me the sign of y26. Okay, so the only thing I need to tell you is what this exponent is here. And this exponent is going to be the area that I see to the left of the arc 2 to 6. Okay, right, so it's the area, I'm denoting it like this. So in this situation, right, so I'm counting how many black triangles are to the left of this arc. I see 2 of them, so my exponent in this situation is 2. So for this arc, I pick up the inequality y26 is positive. And then I also pick up, say, an inequality for y35. There I see 1 black triangle to the left, so my exponent is 1. So I get that y35 should be negative. And those are exactly the inequalities I need to cut out these tiles. Okay, so let me go, I'll finish up by saying this kind of, okay, so we have a complete understanding of the tiles. Let me talk about our kind of complete understanding of the tilings. So, right, what we know is that if we take tilings of the amplituhedron, they're in bijection with so-called tilings of the hypersimplex. Right. I'm going to go a little fast through this because maybe I don't have so much time. So first, okay, so yeah, what is this stuff? So first of all, what's the hypersimplex? It's the convex hull of all 0, 1 vectors with exactly k plus 1 ones in R to the n. It's also the uniform matroid polytope, if that means anything to you. Here in the corner is a small hypersimplex delta 2, 4. Okay, I want to tile it, so let me tell you what the tiles are. The tiles are going to be some polytopes, again indexed by bicolored subdivisions. And these polytopes, well, I can give you an inequality description of the polytope. And the inequality descriptions are going to utilize, they're going to have kind of very similar forms. So I'm going to have one inequality for each arc of a black triangle from my subdivision. And I'm going to, again, use this area statistic to give me the bounds in my inequalities. But now, instead of like talking about twistor coordinates, the thing I'm going to be putting inequalities on are sums of consecutive coordinates in Rn. Okay, so short version is these tiles, they're going to be polytopes. I cook up these polytopes, again, with inequalities that kind of come from my bicolored subdivision. Okay, and what is it? Yeah, they're also positroid polytopes, if that means anything to you. And what is a tiling? Well, it's just a decomposition of the hypersimplex into tiles with disjoint interiors. So exactly in parallel to the amplituhedron definition, just now my tiles are going to be polytopes instead of some polytopes, and also kind of relatively understandable. I know exactly their inequality descriptions instead of these maybe slightly more complicated subsets of GRKK plus 2. Okay, and so the result is, if you have one of these kind of polytopal decompositions of the hypersimplex, these are in bijection with the tilings of the amplituhedron. So here's the picture, the only one I can draw. Here's the tilings of the hypersimplex, right? So this blue guy's a tile, this green guy's a tile, together they form a tiling. And here's the tilings of the amplituhedron. And you can see, indeed, if you take a collection of tiles forming a tiling over here, then the corresponding collection of tiles also forms a tiling over here. Okay, so I think I'll maybe end with saying this. So this result, I mean, okay, so one thing that this result is very good for is it kind of simplifies the study of tilings of the amplituhedron, because instead of thinking about the amplituhedron, you can just think about this polytope, and you have all of the tools of convex geometry and sort of combinatorics of polytopes to help you out. So yeah, it's often easier to prove things by looking at this level. The other thing that's really interesting is that, well, these tilings of the hypersimplex, okay, so inside of those, there's a particularly nice subset, which are called finest regular positroidal subdivisions of the hypersimplex. So exactly what those are maybe doesn't matter so much right now, but these have come up in completely separate contexts to the amplituhedron, like very interesting, worthy of study in their own right. And in particular, this kind of nicest subset of the tilings, we understand its global structure, meaning we have a different combinatorial object which parametrizes all of the points in here. So there's a polyhedral fan called the tropical positive Grassmannian. So, right, a fan is going to be some picture that looks like this. And the maximal cones of this fan, so the full dimensional pieces, like say this one, the maximal cones of this fan are in bijection with these finest regular positroidal subdivisions, so with these nicest tilings. And so, yeah, this is a hint that there's some very interesting structure in these tilings of the amplituhedron, because they sort of have this very nice subset where there's a global parametrizing object, which people who are, for example, interested in tropical geometry find a very nice object to study. Yeah, so, all All right, I won't tell you anything about the proof of the magic number theorem, so I guess you should just know that it's true. I also won't tell you much about what happens in m=4. I'll just say things get a lot more complicated. Tiles are now indexed by pictures that look like this, so more complicated than the subdivisions of the n-gon. When you want to describe a tile, you need more complicated functions. So it's still a region where certain functions have certain signs, but the functions you need to talk about become more complicated. You get some quadratics. Yeah, and I think I will stop there. Thanks so much for listening.
Do you have any questions for Melissa? We can end the recording here, and if people have questions, we can ask off record. Let's thank Melissa again.